Welcome back to the Explainer, everyone. Now, for all you focused learners out there who have ever stared at a piping and instrumentation diagram, a PNID, and felt like you were trying to read some ancient, totally indecipherable alphabet, well, this breakdown is exactly for you. Today, we're going to demystify those complex PNID tags. We aren't just memorizing acronyms here, we're going to connect them directly to the physical, real-world instruments they represent out in the field.
So let's dive right into this. Have you ever actually wondered what is the physical reality behind the alphabet soup of a PNID? I mean, we see these combinations of letters and numbers plastered all over industrial blueprints, but without understanding the steel, the electronics, and the underlying physics behind them, they're really just ink on a page, right? Today, we decode that universal language known as ISA 5.1.
Here's our roadmap for today. We'll be looking at 1. Decoding ISA 5.1 tags. 2. Flow measurement covering FT and FDT. 3. Pressure transmitters focusing on PT and PDT. 4. Temperature sensors like the RTD and TG. And finally, 5. Tracking level with LT, LZT, and LG tags. Let's get right to it.
Section 1. Decoding ISA 5.1 instrument tags. Okay, before we get our hands dirty with the physical devices, we absolutely need the key to the code. The standard relies on a really strict required reading order. You look at the measured variable first, and then the function of the instrument.
So the very first letter of any instrument tag always identifies the initiating process variable in the loop. This tells you exactly what physical property you're actually measuring. F is for flow, P for pressure, T for temperature, L for level, and Z for position or dimension. The second your eyes hit that first letter, you know exactly what physical realm you're dealing with.
But, process control is rarely that simple, which brings us to modifiers. These are letters placed immediately after that primary first letter to tweak its meaning. For instance, a standard PT stands for pressure transmitter. But if we slide a D in there, it transforms into a PDT, a pressure differential transmitter. Just by adding that one single critical modifier, we've changed the instrument from measuring a single point of pressure to actually comparing two different pressures against each other.
Section 2. Flow measurement, featuring the FT and FDT. Let's picture a hypothetical fluid pumping through a heavy steel pipe. How do we actually quantify that movement? Well, we use flow transmitters, or FTs, and sometimes flow differential transmitters, or FDTs.
A perfect example of a physical FFT is the industrial turbine flow meter, like your FT3, 4, or 7 series. Now, these are highly mechanical devices. Inside that tough stainless steel body, there's a helically cut turbine rotor. As the liquid flows, it physically forces this rotor to spin. A pickoff coil with a permanent magnet sits just on the outside. As those rotor blades zip past, they change the magnetic flux, which induces this tiny electrical voltage. The frequency of that voltage is directly proportional to the rotor speed, giving us our volumetric flow rate. This is what lets engineers establish a constant K factor, or pulses per unit of volume. Just keep in mind, these are strictly for clean liquids, usually stuff under 10 centistokes of viscosity.
But what if your fluid is full of sludge, or you literally just can't afford the pressure drop of a physical rotor sitting in the pipe? You use a magnetic flow meter, and this brilliantly illustrates Faraday's law of induction. The meter applies a constant magnetic field across a completely open, obstructionless flow tube. If the fluid is conductive, it's packed with positive and negative ions. As this conductive fluid rushes through the magnetic field, the force shoves the positive ions to one side of the tube and the negative ions to the other. It's exactly like magnets repelling. This separation creates an electrical voltage picked up by electrodes. The faster the flow, the stronger the voltage. It's incredibly accurate. And the best part? Zero moving parts.
Section 3. Pressure transmitters. Looking at the PT and PDT. All right, let's shift gears from the flowing fluid itself to the highly pressurized environment of the pipe holding it.
It is absolutely crucial to understand the difference here. A PT, or pressure transmitter, measures a single process pressure source. It gives you a raw reading relative to atmospheric or absolute zero pressure. But a PDT, which, by the way, can also function as an FDT, or flow differential transmitter, when you pair it with an orifice plate, doesn't care at all about the raw pressure. It measures the difference between a high plus side and a low minus side. It's internally calculating delta P, which is just the high pressure minus the low pressure.
Now, what's really interesting about this is how a device like the Pondus PT600 actually survives the harsh, violent reality of a chemical plant. It uses a central piezoresistive sensor hooked up to two oil-filled membrane chambers via capillary tubes.
But let's face it, industrial processes are wild. Pressure can spike out of nowhere. To handle that, the Pondus uses a dedicated mechanical overload membrane. This brilliantly protects the delicate sensing element by physically limiting the differential pressure during massive surges up to 150 bar. So even if the pipe takes a destructive field spike, your sensor is perfectly safe. It even has a handy little auto-zero function, so you can recalibrate effortlessly right after installation.
Section 4. Temperature sensors, specifically the RTD and TG. Okay, so we know the fluid's speed and its pressure, but how much heat is it actually carrying?
Back to our ISA 5.1 standard, the first letter T represents temperature. And the RTD, the resistance temperature detector, is pretty much the gold standard here. Unlike a simple glass thermometer, an RTD measures temperature by utilizing the highly predictable way that certain metals change their electrical resistance when they are heated up or cooled down.
If you're out in the industry, you're going to hear the term PT100 constantly. That number 100 isn't arbitrary. It's a literal physical baseline. It tells us that the platinum sensor inside that device will output exactly 100 ohms of resistance when it's sitting at exactly 0 degrees Celsius.
Because this physical relationship is so incredibly precise, technicians can rely on standard lookup tables. For example, if a pipe's actual field temperature is 30 degrees Celsius, the RTD has to output exactly 111.8 ohms. If an engineer checks the PLC, the programmable logic controller, and it reads 111.8 ohms, boom! They know with absolute certainty that the RTD is perfectly calibrated.
Section 5. Tracking level, featuring the LT, LZT, and LG. Finally, let's move to our last major process variable. Our fluid has traveled the entire pipe, and it's now collecting in a massive tank.
Here we really need to contrast the LT and the LG. An LT, or level transmitter, is an automated workhorse. It continuously measures the height of the fluid and sends a standard 4 to 20 milliamp electronic signal back to the central control system, meaning valves can be opened or closed automatically. An LG, or level gauge, on the other hand, is old school in the best way. It provides direct, physical, manual verification. It's usually a thick glass tube right on the side of the tank where an operator can literally walk up and see the fluid level with their own 2 eyes.
Let's see how this builds. We can actually take this even further with the LZT. By combining L for level with the modifier Z for position or dimension, ISA 5.1 lets us create highly specialized tags. An LZT isn't just looking at the overall volume, it's a level position transmitter designed to track highly specific positional boundaries or physical dimensions of the fluid interface within that vessel.
But here's a really cool trick. How do we actually measure the level inside a highly pressurized, completely sealed tank where we can't just look inside? Well, we actually borrow a tool from our pressure section. We use a differential pressure transmitter, like the hygienic Pondus PT60 Type T. The high-pressure plus side is attached to the very bottom of the tank, measuring the total weight, the hydrostatic head, of the liquid plus the pressurized gas pushing down on it. Then, the low-pressure minus side is connected to the top of the tank, measuring only the gas pressure. The transmitter mathematically subtracts the gas pressure from the total, cleanly canceling it out, and outputs a true, highly accurate liquid level reading. And because it's a Type T, it uses sanitary, clean-in-place connections that are absolutely perfect for the food and life science industries.
So what does this all mean for us? It means the crucial takeaway is that every combination of letters on a PNID is tethered to actual physics and real, tangible mechanical designs, which leaves us with a question to test your new knowledge. If you were out in the plant right now, how would you troubleshoot an FIC, a flow indicating controller, or a PDT tag? Think about those rotors spinning, the magnetic field separating ions, and those oil-filled membranes taking the hit. Next time you look at a PNID, remember, you aren't just reading letters, you're literally looking at physics in action. Thanks for joining this explainer, and keep learning.